There are two different types of rate of change. One of them is the average rate of change. The average rate of change is like when we find the gradient of something. It is the rate of change between 2 points. So we use y2 minus y1 over x2 minus x1. The instantaneous rate of change is the rate of change at a point. It is not over an interval. So it is always at a point on the graph. So in example 3, we have the function 2x squared plus x, and we want to find the average rate of change between 2 and 3. So we're looking for the rate of change over that interval. So we need to find f of 3 minus f of 2 over 3 minus 2. So it is your y values, y2 minus y1 over x2 minus x1. So let's work over here and work out what f of 3 is. We're substituting it into our rule and we get 2 times 3 squared plus 3. 3 squared is 9 times 2 is 18 plus 3 is 21. What about f of 2? f of 2, substituting it into our function, and you get 2 times 2 squared plus 2 is equal to 2 squared is 4 times 2 is 8 plus 2 is 10. This is now ready to put into our rule. So f of 3 we know is 21. f of 2 is 10 over 3 take away 2. Let's tidy it up. That gives us 11 over 1, which is just 11. So the rate of change, the average rate of change between 2 and 3 is 11. And you can see over here that this is something that we can also do on our calculator. Average rate of change is a function on our calculator. We put in the rule and then we put in the actual interval. Something really important to notice when you are using that rule on your calculator is this number here. So 2 is your starting point, and the distance or the difference between the two is 1 because we're going from 2 to 3. Still looking for the average rate of change for that function, but this time it's between 2 and 2 plus h. So we want f of 2 plus h minus f of 2, remember that's your y2 minus your y1, over 2 plus h minus 2. That's your x2 minus your x1. Let's do some working out over here. F of 2 plus h. Remember the rule was f of x equal to 2x squared plus x. So f of 2 plus h would be 2 times 2 plus h squared plus 2 plus h. Let's expand that out. 2 times 4 plus 4h plus h squared plus 2 plus h. And so we get 2h squared plus 9h plus 10. Let's do the same for f of 2. So f of 2 is equal to 2 times 2 squared plus 2. We'd already worked that out previously, hadn't we? And so that's 2 squared is 4 times 2 is 8 plus 2, which is 10. And we are now going to put that into our rule. So f of 2 plus h is 2h squared plus 9h plus 10. Take away f of 2, which is just 10, all over. And of course those two cancel and we're left with h, and those two cancel. So we can take out a common factor of h here, and we've got 2h plus 9 over h. They cancel and I'm left with 2h plus 9. That is my final answer. When finding the instantaneous rate of change, we are going to use the derivative. It is not over an interval, it is at a point, and the point that it's at is x equal to 2. So we are going to do d dx of 2x squared plus x at x equal to 2. So that is going to find us our instantaneous rate of change. So let's do d dx first of all, and that's 4x plus 1. And again, it's at x equal to 2. So at x equal to 2, we're going to substitute it in, and we get 4 times 2 plus 1, which is equal to 9. So our instantaneous rate of change at x equal to 2 is 9. A balloon develops a microscopic leak and decreases in volume. Its volume, v centimetres cubed at time t seconds, is given by v equal to 600 minus 10t minus 1 on 100 t squared, and t is greater than 0. Now the question asks us to find the rate of change of volume after 10 seconds and after 20 seconds. So we want them at a point, not between an interval. So the first one here is at 10 seconds. So what we're looking for is dv dt, the instantaneous rate of change at t equal to 10. So let's find dv dt. dv dt is equal to, okay, 600 becomes nothing, so minus 10, and I get minus 2 on 100 t. We should be able to differentiate them fairly easily now. All right, and we want it when t is equal to 10. So let's substitute in t equal to 10, and we get minus 10 minus 2 on 100 times 10, okay, and that simplifies down to minus 10 and 1/5. All right, the next one, we are now looking for when t is equal to 20. Now our derivative is still exactly the same. So dv dt is still going to be negative 10 minus 2 on 100t, but this time I'm substituting in the 20. So negative 10 minus 2 on 100 times by 20, and when you work all of that out, you get negative 10 and 2/5. So the instantaneous rate of change at t equal to 10 seconds is negative 10 and 1/5, and the instantaneous rate of change at t equal to 20 seconds is negative 10 and 2/5. So we can say that the volume here is decreasing by, so volume decreases by 10 and 1/5. And what are the units? Centimetres cubed per second. Same thing for this one over here. The volume decreases, so volume decreases by 10 and 2/5 centimetres cubed per second. So units are important. Part B asks us how long would the model be valid. Now let's have a look at our function for volume. Volume is pretty much a quadratic. So therefore, the only part of the quadratic that we want is when t is greater than 0. So although that is the diagram for the whole volume, if there were no restrictions, because there are restrictions, then I only want that part of the graph. So I'm only going from there to there. And again, I don't want anything underneath the graph because that would not be part of the graph. We don't want our volume being negative. So we want time to be positive and we want the volume to be positive. So we're looking at these 2 points here. All right, well, obviously they are intercepts. So how do we find intercept? Well, to find t-intercepts or x-intercepts, we let y equal 0. So here, the t-intercepts, we're going to let v equal to 0. So let's let our equation equal 0. 600 minus 10t minus 1 on 100 t squared is equal to 0. Now, not overly nice. We could throw that straight into a calculator and get an answer, or we could use the quadratic formula, and the quadratic formula would look something like this: 10 plus or minus the square root. Remember, it's b squared minus 4ac, so it's 100 minus 4 times 0.01 times 600. It's all under the square root, and that's all divided by negative 0.02 minus b plus or minus the square root of b squared minus 4ac on 2a. Okay, you still probably need your calculator to do that anyway, and so when you work that out, you get t is equal to negative 1056.78, or t is equal to 56.78. Now I've just gone to 2 decimal places there. Obviously, the negative one we don't want, because we know that this model is only going to be valid between 0 and this point here. And we've just worked out what that point is, 56.78. So therefore the model is suitable. It asks for how long would the model be valid. The model would be valid between t is greater than 0. Remember, it wouldn't be valid at 0, so they are open circles if we were drawing our graph, and between 56.78. We do want our volume to be greater than 0, not including. So that's why we're not including those endpoints. So valid between t is equal to 0 and t is equal to 56.78.